All right, I would like to now introduce Dr. Caren Binding, our speaker for today. She is a research scientist with Environment and Climate Change Canada at the Canada Centre for Inland Waters in Burlington, Ontario. And her research focuses on aquatic optics and satellite remote sensing for water quality applications. She's worked on Lake of the Woods since 2009, developing remote sensing tools for detecting algal blooms, and is the lead on EO Lake Watch, which you're going to get a taste of today. It's a platform for delivering publicly accessible satellite-derived products for algal bloom monitoring. I think you're going to find this just fascinating. So thank you so much, Caren, for joining us, and take it over.
Okay, thanks very much, Kelly, and thanks to you and Todd for the invitation to present today. Yeah, I'm going to be talking a little bit about the work we've been doing over the last few years, developing satellite remote sensing tools for detecting algal blooms on Lake of the Woods. You've likely all seen striking satellite images like this that really nicely capture the color intensity of blooms and help to visualize the extent of the problem on Lake of the Woods. But what I'm hoping to do today is walk through how we're using imagery like this to extract quantitative measures of the blooms. And I'll demonstrate to you how you're able to access some of the products that we produce to keep up to date on the status of bloom conditions on the lake. And I'll show how we use those products to further understand trends and drivers of bloom conditions on the lake. Before I go any further, I wanted to just acknowledge the rest of my team here. So Larissa, Tree, and Colleen, they've been instrumental in helping to move this work forward and provide operational support. So we know that Lake of the Woods continues to experience severe algal blooms despite declines in external phosphorus loads. There's concerns over socioeconomic and ecosystem impacts of those blooms, from tourism and recreation impacts to the aesthetic value of the lake, impact on local fisheries, and particularly public health concerns over toxins related to cyanobacteria. And so with ongoing blooms, there's a recognized need for consistent lake-wide and objective monitoring of algal bloom conditions. We heard from Jesse last week, the Minnesota waters of Lake of the Woods were declared impaired in 2008 due to exceedances of eutrophication criteria leading to their TMDL study. And then in 2016, ECCC was funded for their Lake of the Woods science program. So this is an integrated research and monitoring program designed to provide the necessary science to support future binational decisions and management actions to reduce eutrophication and algal blooms on Lake of the Woods. And it's under this program that our work has been funded in the last few years. So just as a brief background, satellite remote sensing of water quality in general is based on the concept that variations in the composition of water can lead to measurable changes in the color of the water. And so the satellite imagery that we're interested in measures aquatic color from across the UV, visible, and near infrared portions of the spectrum. It's what we term passive remote sensing because it measures the response of the water body to solar illumination. And so this graphic here describes the process that we're measuring. So light penetrates the water body and interacts with dissolved and particulate material in the water column through processes of absorption and scattering. And so some of that light is then scattered back through the water column, through the atmosphere, and is picked up by the satellite sensor. And so it's that water leaving radiance signal that contains all the information that we need to derive concentrations of the colored water quality variables we're interested in. So chlorophyll, other phytoplankton, pigments, suspended minerals, dissolved organic materials, and under some circumstances, depending on the light penetration, we can also look at substrate and submerged aquatic vegetation. So just a little background here on the satellite platforms that are available to us. There's been a number over the decades. The main focus of them is to look at either land or global ocean color. These sensors have a variety of different spectral resolutions, you can see on the left there. So going back to the first experimental sensor, the CZCS, it had just a handful of color bands available on it. And then over the decades, we've had increasingly sophisticated sensors available to us, to the point that more recently, current and some planned sensors use hyperspectral technology, so scanning continuously across the spectrum. As well as the spectral resolution, these sensors vary in the spatial resolution. So more recent sensors like the Sentinel-2 here measure at about 10 to 60 meter spatial resolution. Others like MODIS, CRIFS are much coarser and measure at about a 1 kilometer spatial resolution. These sensors are polar orbiting typically, and meaning that they rely on the Earth's rotation to allow successive orbits to scan different areas of the Earth. So over time, it builds up a global coverage of observations. And so all the satellite sensors that you see in that table there, data is provided in a free and open access model, so making very much a low-cost observation tool. So here I just show a schematic that describes some of the methods we've been, some of the work we've been doing to develop our methods rather over the last few years. So a large part of the work that we do is in aquatic optics. So we use a suite of field and lab instrumentation to measure how light interacts with dissolved and particulate materials, so the phytoplankton themselves in the water column. And that allows us to spectrally characterize the blooms in the same way that the satellite sensor does. And with that in-lake sampling combined with optical theory and modeling approaches, we're able to develop algorithms to derive chlorophyll A as the primary pigment indicating phytoplankton biomass or algal bloom biomass. And so applying those algorithms to the raw satellite data, we're able to produce maps and extracted data products to track the bloom. And then finally, we use independent bloom measures to validate quality control on our products and, where necessary, refine our algorithms going forward. So why do we use remote sensing? What's the benefit of in-lake sampling? We know that Lake of the Woods is challenging to monitor. Its size, the navigation hazards, the hydrological complexity of the lake mean that it's difficult to get out on the lake and do intensive sampling. So our water quality monitoring division do annual surveys on the lake, and they typically take 2 to 3 weeks to capture roughly 30 core water quality stations on the lake. But we know that blooms are highly dynamic in nature. They can be localized or lake-wide. They can form small-scale surface scums. And so you can see in the images below there that the bloom distribution can be quite patchy. And so it's really challenging to capture that spatial variability with in-lake sampling. And equally, it's challenging to capture the temporal variability and the timing of blooms within lake sampling. So the graph on the left there shows the lake average chlorophyll concentrations for a few years, and the red vertical lines show the timing of our fall lake survey. And so you can see that some years you might capture the peak bloom severity, and other years you might not capture that peak. So add to that the day-to-day variability in bloom conditions. So on the right, you see 2 consecutive days where on the first day, there's quite an intensive bloom covering most of the lake. And the next day, with winds blowing from the south, that bloom was driven onto the north shores. And so you can imagine if you're out on the lake, it depends very much on when and where you're sampling as to what bloom conditions you might encounter. And then I guess with COVID-19 restrictions over the last couple of years, that's really reduced the monitoring and fieldwork capabilities on the lake. And I think more than ever highlights the real value of remote sensing to deliver uninterrupted monitoring solutions. So with all those advantages, there are limitations to remote sensing. So with it being an optical sensor, it doesn't penetrate cloud. So you can see in those example images on the bottom there that cloud obscures the view, and so it results in spatial and temporal data gaps in observations. Because of the light penetration into the water column, the satellite only sees near surface conditions, and so we don't get a whole lot of information about what's happening at depth. And we're only able to retrieve optically active variables, so those that directly impact color. So we don't get information on things like nutrients or toxins, and for that we continue to rely on in-lake sampling. And then the value of the satellite platform really depends on the sensor specifications. So the differences in revisit time, the spatial resolution, the spectral resolution. And so different sensors can result in different quality of retrievals and the frequency of available imagery. So over the last few years, we've been able to develop a system in-house to fully automate near real-time access to satellite imagery. So this slide shows the workflow that we follow here. So we access data from two satellite streams. So the European Space Agency MERIS data from 2002 to 2011, and the Sentinel-3 Ulchi dataset from 2016 to present. And with high performance computing and cloud storage, we're able to download that imagery on a daily basis and apply our algorithms to derive daily imagery of chlorophyll concentrations. And then to minimize the cloud-related data gaps, what we do is combine multiple days into a 14-day average chlorophyll map. From that, we're able to define a bloom area. We use a chlorophyll A threshold of 10 micrograms per liter to do that. And that's consistent with World Health Organization guidelines of mild or low probability of adverse health effects under conditions of cyanobacteria dominance. So it's also in line with NPCA's guidelines as well. And from that, we're able to extract quantitative bloom indices that document the bloom spatial extent, the bloom intensity as the average chlorophyll content of the bloom area, bloom severity as the product of extent and intensity, and then bloom duration as the number of days that any particular location experiences a bloom over the monitoring season. And so that process exports time series data products, mapped data products that we push to EO Lake Watch platform. So this workflow runs in a fully automated manner on a daily basis from June through October every year, and every day those products are pushed to EO Lake Watch, which is a web platform that was launched last year to allow the public to access those data products in real time. And I'll walk through the web material actually in the next slide. So here on the landing page, you're able to access some background information on remote sensing of algal blooms, the government programs that it supports, and a brief description of the methods we use. And then if you go back to the main menu, you can access the interactive algal bloom monitoring tool here. And you can select your lake of interest and it will update with the latest bloom map for that area. So what we see here is the latest 14-day average chlorophyll map, and the chart below is the time series of the selected bloom index going back to 2002. And so you can select on any point on the graph and the image will update to that day, and the pop-up window will give you the daily bloom indices for that day as well. You can change a selection for the bloom index that you're interested in, and it'll update the chart below. And then the time slider allows you to zoom into a particular time period that you're interested in for a more detailed look. And again, you can click on any point along that graph to view that day's image and the statistics for that. So then this button down here allows you to download the content of the portal in a variety of different formats. And then below the portal, there's a list of the kind of commonly used terms. There's a link there to our annual bloom reports. So there's a bit of a brief interpretation guide on the top, and then links to the annual bloom reports dating back to 2002 there again. There's also a frequently asked questions. So if you want to learn more about the sensors we're using, the methods, or links to data access and terminology generally, you can find that there. And there's a image gallery where we've posted some of the more interesting true color images that you can view and download in high resolution. And then there's contact pages and the link to subscribe. So if you're interested in receiving weekly bulletins on bloom conditions and receiving that annual bloom report, then you can enter your details here and subscribe to our mailing list to receive those. And so here's an example of our annual bloom report. This is from last year. On the left is the first page of that report, where you see daily bloom indices on the left side here, showing the progression of the bloom. And on the right is the annual average bloom indices. So in green for the reporting year, and the black bars showing the historical conditions. So here we can see that last year's bloom was slightly above average in bloom spatial extent, but a little below average in intensity and overall severity. And then the second page of the report shows the mapped products. So on the left here, the bloom duration in days, and the right is a map of chlorophyll on the day of peak bloom severity there. And below is the tabulated results, so showing the average and peak bloom statistics for that year relative to the long-term average. So this year's bloom report, so we're still in the final stages of the monitoring season now. This year's report will be issued towards the middle of November this year. So here I've tried to capture this year's bloom progression to date. So on the right is the latest weekly bulletin for Lake of the Woods. So it shows the latest 14-day average chlorophyll concentrations, and then a graph showing the progression of the bloom spatial extent. So in red for this year, and then the average, historical conditions in black and gray. So the black being the median and the gray being the 25th and 75th percentiles. So we can see here that the bloom tracked well below average throughout July and August. You can speculate though that the wildfires at the beginning of the season there, the thick smoke and haze that was produced obscured quite a lot of Lake of the Woods for a number of days. And so that might well have had an impact on the late start of the bloom this year. But we can see come early September, there was a rapid increase in the bloom spatial extent, but still tracked a fraction below average right up until the beginning of October here. And then on the left here, I'll show an animation that shows the spatial variability of the bloom so far this year. So on the top left here is the date, and you'll see that change over the course. So at the beginning of the season, there was some isolated bloom activity in Mawson Bay and north of Big Island there. But after that, throughout, like I said, most of July and early August, there was very little activity on the lake. And that's until the middle of August here, where blooms start to pick up in Sabascong, Miles Bay, north of Little Traverse and the Big Narrows, and then begins to extend into Big Traverse there towards the end of October, early September. Here, the first week of September, you can see the bloom extending well into the north of the lake towards Kenora. And then the bloom intensifies towards the end of September in the Big Traverse. And as winds drive the bloom onto that north shore of Big Traverse towards the end of October. And so this year we were able to get back out onto the lake for a reduced field campaign. Our water quality monitoring division were out in September and did a full lake-wide survey of their core water quality sites. And then in early October, we were able to do some targeted image validation samplings. So that was in the Big Traverse and Mawson Bay area. So we used up-to-date imagery to try and target the most intensive bloom conditions, and we were able to do that on a day-to-day basis. So the photos on the right there show some of the bloom conditions that they were sampling in. And so at those sites, we were able to sample for chlorophyll A and other phytoplankton pigments, phytoplankton taxonomy, toxins, and optical properties. And so we're analyzing that data at the moment, and we'll use that to continue validating our retrievals. So looking back at historical conditions here, I've compiled the maps of chlorophyll at the peak bloom severities. So for dating back to 2002 in the top left corner to this year in the bottom right. And so you can see a fair bit of interannual variability in the bloom conditions. 2003 and 4 jump out as particularly severe years, especially in Sabascong and the Big Traverse. But then other years, you can see that the bloom is quite severe in the north. So 2005 through 7, there was severe blooms across the north. Mild bloom years jump out, particularly as in 2008, 2018, 2019. You'll notice that there's an image gap here for 2012 through 2015, and I'll come back to that in a later slide to discuss that more. So here we're looking at temporal trends, and so we've extracted the annual bloom indices, so extent, intensity, duration, and severity. These are lake average, in blue, season average, and in gray, the season maximum indices. And what we're seeing is significant decreases. There's a fair bit of interannual variability, but there are significant decreases in some of those indices. So suggesting perhaps that the lake is beginning to respond to historical nutrient reductions. And although our season hasn't quite yet come to an end, I've added on here some preliminary bloom indices for this year. So we're seeing the maximum extent fairly consistent with last year. The average is quite a bit reduced, and because of that latest start than usual to the bloom. The bloom intensity, again, is fairly consistent with observations from last year. And so here we tried to look at more regional trends over the lake. So we looked at averaging annual chlorophyll concentrations for 12 designated zones across the lake. And so these bar charts show like I said, the annual chlorophyll concentration for each zone. They're color-coded according to the chlorophyll range. So the highest range we see on the lake is across the southern portion of the lake from Sabascong, Mawson, Big Traverse, and Little Traverse. The green is the middle chlorophyll range, and we see that through the main flow of the lake, up northwards up to Kenora, and then the blue is the lowest range. So more in the isolated bay, so Whitefish, Big Stone, Clearwater. And in terms of trends, what we see is a suggestion of a significant decrease in chlorophyll in those regions that, again, follow the main flow of water in the lakes. So from Mawson, Big Traverse, Little Traverse, again, up through to Kenora, whereas the more isolated embayments here, Sabascong, Whitefish, Northwest Angle, Clearwater, they show no significant trends at the moment. We'll be updating these analyses with more recent observations as well, and it'll be interesting to see if those trends continue. So we've been using our products as well to look at a suite of environmental drivers of blooms on the lakes. So our results support the fundamental relationship between blooms and in-lake phosphorus concentrations. So that graph on the right there shows a scatter plot of satellite-derived chlorophyll and lake average total phosphorus. Interestingly, the range of state and provincial phosphorus guidelines there highlighted in pink is in good agreement with the 10 micrograms per liter of chlorophyll that we use as a threshold. What we find, though, is that there's no positive correlation with annual phosphorus loads from the Rainy River. And we heard from Jesse last week that those tributary loadings contribute about 40% of the total phosphorus budget in the lake. And so our results support then the role of those additional nutrient sources, particularly internal loading in driving those blooms. So unlike in other lakes like Lake Erie, where the bloom severity can be reasonably forecasted by spring TP loads, it's a lot more complicated here on Lake of the Woods. What we have found, though, is that there's significant climate drivers of blooms on the lakes. So in a previous analysis, we found that severe blooms occur during warm, dry years, with low blooms in cool, wet years. And what we find consistently in our imagery is that bloom location is determined quite often by wind-driven surface advections. So here there's a time series of imagery that demonstrates that quite nicely. So on the top there is the wind data, wind direction and wind speed from Kenora, and below a series of our satellite-derived chlorophyll. On the left, towards the end of September this year, we saw light winds from the north, which allowed an intense bloom across the whole of the Big Traverse and Little Traverse. A few days later, we had strong winds from the south that drove that bloom onto the north shores. And then a few days later, again, the winds swung so easterly is driving that bloom material to the west of the lake, and then again returning to strong winds from the south that drove it north. And what we're trying to do with this information, actually, and recognizing that the wind field is quite complex around Lake of the Woods, is using a range of data sources on wind to try to get at a short-term bloom forecast on Lake of the Woods. Another impact of wind is the vertical mixing. So with the low light penetration, our satellite observations really only get at a surface measure of algal blooms. And so we don't really know a whole lot about what's happening below the surface from the satellite images. We also know that cyanobacteria are able to regulate their buoyancy. So under calm weather conditions, allowing intense surface blooms to form, and then with wind events mixing that biomass through the water column. So the depth profiles you see there show that surface accumulation of chlorophyll A under low wind conditions, and then it mixing through as wind speeds pick up. And so what that means for our image products is that we capture that day-to-day mixing of bloom biomass through the water column as wind speeds vary. In terms of climate drivers, we know that Lake of the Woods, winters are getting milder, the ice-free periods are getting longer. And what we're seeing in our data sets is that blooms appear to be peaking later in the year. So the bar graph on the top there shows the change in the day of the maximum bloom severity. We find that severe blooms peak early in the year and milder blooms peak well into October. So the image on the bottom right there is a Sentinel-2 image from 2017 that captures the blooms still very much present towards the end of October. And we know those blooms to be often dominated by cold water tolerant bloom species. And then, so I mentioned earlier the observation gap between 2012 and 2015. And so at the moment, the two satellite sensors that we use offer us consistency in the sensor specifications, so giving us confidence that there's continuity in the products that we deliver. And so seeking another data set that allowed us to fill that gap, we turned to MODIS. It has different spatial and spectral sensor resolutions, so it's not ideal, but it allows us to fill that observation gap. And so we've developed some novel neural network algorithm approaches to develop a chlorophyll retrieval that is consistent with our existing sensor data sets. And so we've been able to fill that data gap here. This is for bloom extent, and we're applying that across to the board to the other bloom indices, and we'll be updating our trend analysis accordingly. And so to summarize, I've shown that satellite remote sensing provides a low-cost solution for lake-wide bloom detection. With the launch of EO Lake Watch last year, we've been able to deliver prompt and comprehensive decision-ready products for reporting on bloom conditions. We've used those products to better target in-lake monitoring, assess trends, and identify areas of potential concern. We've analyzed bloom drivers and demonstrate the complex interaction of nutrients, both external and internal, and the seasonal weather variability and climate change impacts in determining bloom severity on the lake each year. And then finally, those products have been used to inform policy and decision making. And so helping to define lake ecosystem objectives and indicators and nutrient management scenarios, and moving forward is an ideal tool to monitor the effectiveness of actions to reduce phosphorus and lower algal blooms on the lake. So that's all I have for today. A reminder, if you'd like to receive updates on bloom products for the Lake of the Woods, then you can sign up for updates on the website, or feel free to email us on the emails here on the slide. But otherwise, if you have any questions, I'd be happy to address them.
Thank you so much, Caren. Looking in the Q&A, we do have 2 questions from Paul Anderson. Paul, would you like to ask Dr. Binding your questions?
Oh, could you please unmute?
Okay, this time.
We can hear you.
Okay. No, my same question that I've asked before. What are the plans for the rest of the watershed, and what does it take to add a lake or two to this overall effort from dollar or person hour point of view? Thank
Right.
you.
So yeah, in the past, we've been fairly limited to a number of priority large lake systems, partly because of computing infrastructure. But this year, we've actually migrated our processing system to a reliable high performance computing environment and cloud. And so we no longer have those limits. And so we're exploring options to include additional lakes to expand the region's interest. And we're also working on a portal version 2. So that is going to be allowing a lot more user flexibility in terms of where bloom indices and observations are retrievable from. So you can zoom into the lake and select a pixel or region of interest and look more closely there. So we are working actively to incorporate additional lakes, and if there is a particular lake of interest, then I would welcome hearing from you. But there are some limitations in terms of the size of lake that we're able to confidently monitor. So a very small lake with the current suite of sensors that we're using might not produce reliable results at the moment, although we're exploring some other sensor solutions for that application. Yeah, hopefully that answers.
Paul, any follow-up?
Oh, thank you. That's great. Appreciate it.
You're welcome.
Thank you. We have a question in the Q&A from an anonymous attendee. Would you like to unmute and ask yourself?
Don't know that's possible, Kelly.
Okay, sure. So I'll ask it, Caren, for you. First of all, the person thanks you for a great presentation and says, I wonder if your method is applicable to smaller lakes, let's say a few kilometers in width and length. What would be the limitations, as I think the spatial resolution should be finer? Are Landsat and Sentinel suitable to provide this information?
Right. Yeah. So so spatial scale, like I said, is a limiting factor. So the products that we're using with Mulchi and the current data stream is a 300-meter spatial resolution. Sentinel 2, as you mentioned, has that 10 to 60-meter spatial resolution that is far more suitable to small water bodies and the very near shore observations. Sentinel 2 does contain the spectral information that we need to be able to adapt our algorithms to apply to that. And so that's an active area of research for us to be able to incorporate that data stream into our work to provide the high resolution imagery. The challenge with that sensor is that the observations aren't as frequent. So there's always a trade-off with sensor design, in that with the coarser resolution, we're enabling daily observations. With a higher resolution, you sacrifice that revisit time. So you might not get an image, the revisit time of 5 or 10 days for Sentinel-2. In terms of Landsat, I would say that the historical Landsat sensors have challenges because it's a land-based instrument. It has challenges with the radiometric accuracy over water. So it's not as sensitive as some of these ocean color sensors. The more recent Landsat series, Landsat 8 and the proposed extension to that, are certainly more suitable to water applications, but they don't contain the same spectral information that we need for consistency in our algorithms. And we're trying to make sure that, a chlorophyll concentration that you retrieve from one sensor is has some continuity to what is retrieved from another sensor. So yeah, that's hopefully answering that.
Thank you, Caren. I see that Michael Riley has his hand up. Could you unmute and ask?
Can you hear me?
Yes.
Yeah.
Okay. Early explorers on Lake of the Woods 250 years ago report seeing algae blooms. They report that the lake was green in mid to late summer. But it seems to be, why is it viewed as a problem now?
Yeah, and I think it's acknowledged that Lake of the Woods has historically been a very productive lake, and you know that is to some degree causing us to urge caution in the expectations that it might, you know, clean up to a great degree. But the concern now is that I guess there's a few concerns. One is that there's perhaps a shift towards species of greater concern. So in sedimentary cores, colleagues have noted that since the year 2000, there's been records of increasing cyanobacterial toxins in the sediment. And so with climate change, there's concerns that a shift in the species composition of that bloom might cause greater concern from a public health perspective, and the cyanobacterial toxins that they contain.
Do you have any follow-up, Mike, or is that fine?
No, thank you.
Okay. Thank you. We have a question in the Q&A from Andrea Zapp. Would you like to unmute, Andrea?
Am I unmuted now?
Yes.
Yeah, I just wanted to know, because you were talking, Caren, about like sensitivity and resolution. When it comes to sensors in the lakes, you know, what's more important when you're looking for ground truthing, like to, you know, match it up to your satellite imagery? Is it, you know, sensitivity? Do you want it to go down to a certain dynamic range, or is that not so important?
Great question. So I think, like I said, there's always a trade-off in the sensor specifications that you have to land on depending on the application of interest. So for Lake of the Woods, I always argue that the revisit frequency is very important. Knowing the dynamic nature of blooms, having that daily or near daily observation of bloom conditions is important. The dynamic range, I would argue in less turbid eutrophic waters, the dynamic range is important to certainly over water applications. It's somewhat less important in these conditions where the water signal is very bright because of the enhanced scattering from the phytoplankton. So we're essentially at times looking at land level signals here. So the dynamic range is perhaps less important in this application, but generally for water, it is important to have that sensor sensitivity and what we call the signal to noise quite high for water applications.
With turbidity, sure. And I guess just because I've been doing some reading on how I guess some papers are out there that when some people measure the chlorophyll A with one of the phycobilins, like phycocyanin, but sometimes it might be maybe a more complete total algae sensor if you include the phycoerythrin as well. And I just found some papers that kind of support that? Have you found anything like that in your studies?
Yeah, great question. So, so I think for ficosine, there's a range of algorithms that have been developed and tested to retrieve ficosine from remote sensing. There's a few challenges there. One, that the signal is reduced relative to a chlorophyll A signal, and so you have to rely on a very sensitive sensor to detect that. And also, in terms of a kind of Cal-Val perspective, ficosine isn't as frequently measured in situ to provide a data set for calibration, whereas chlorophyll is very standard measurement approach. And so from phycoerythrin perspective, we've actually been measuring on the lake fluorometry-based algal community composition flow-through system. So over the course of the years, we've accumulated a pretty impressive data set of the phycoerythrin and phycocyanin dominant biomass. And so we're using that data set to look at either statistical or machine learning type approaches to try and tease out that community composition based on a pigment analysis. The challenge, I think, with phycocyanin and phycoerythrin at the moment is that the band combinations on existing satellites don't always align to be able to specifically target that. And so with the hyperspectral technology that's coming with future sensors like PACE, that's exactly what we're hoping to be able to target, is those specific pigment signatures to get at more detail of the bloom composition.
Mm-hmm. Okay, awesome. Thank you for that.
You're welcome.
Caren, it's Todd. I have a question. And you presented information looking at the effects of wind and other variables on bloom formation and on your indices. You also spoke to the interannual variability.
Mm-hmm.
And given that interannual variability on both climate, meaning temperature, and weather, meaning wind,
Mm-hmm.
What's your feeling about the use for effectiveness monitoring as we move into a sort of a management action phase, and sort of what sort of timescales do you think this would be best applied?
Yeah, absolutely. So teasing out that late response in terms of nutrient and climate drivers is going to be the path forward. So you know, the amount of interannual variability you've seen that is driven by combination of nutrient internal and external loading and those climate and weather variables. And you know, we've found from previous analyses that we can kind of somewhat tease out the climate signal, but I think what we're hoping to do is, with the now expanded time series that we have, is go back and do a full reanalysis of those climate drivers and nutrient drivers, and do a more comprehensive study to try and see if we can tease out those signals. And then, yeah, going forward, it's certainly going to take, you know, several years, decades to be able to definitively say, I think, if nutrient responses are being seen.
Thank you. And yeah, and you know, I can certainly clearly see the utility of this, but it's going to have to be at a medium long-term time scale to filter out. For example, 2018 was
Yep.
so windy in August, September, you could barely get a boat on the lake.
Yep.
So that's sort of one hard point in my mind that would have to be you'd have to be looking at this at a long enough time scale. or have some mechanism to filter that out. But
Absolutely.
I think the value of this is, I mean, I think it's stunning. Just a follow up, and I see that you presented that you had done some work to try and fill in the data gap years with the MODIS data. And you noted that sort of a trend analysis update was sort of ongoing. Just a rough eyeball of that to me looks like it might have an impact on the trend showing a reduction in bloom indices over that time scale. Looks like it would flatten that trend out a bit to me.
Yeah, and that was, so that time series was for bloom spatial extent, which I would think will be likely the last index to show a response, in that extent is based on a presence absence measure, and the bloom is either there or it's not, and we calculate the area of that. And so what we're seeing is a stronger decline in the bloom intensity, so the average chlorophyll content of the bloom, and we do still, I think, maintain that trend with the MODIS data in the bloom intensity. So yes, but I agree, the blooms in the I think it was 2014 and 15 were fairly substantial, and so have lifted that trend in the bloom extent. But yeah, we'll go back and reanalyze those, especially it'll be interesting on that regional level within the different zones on the lake to see the impact of that.
Very good. And just as a final comment before we turn to David Malahar, you know, if indeed there is that trend towards reduction intensity, that I think somewhat supports some of the work that folks in Mark Edlin, in particular, the Science Museum, has done on the internal loading component, showing that that is bleeding off over time. And also Bev Clark has recently done an analysis of the Ontario Lake Partner data for a site where there's a long-term record of seasonal data off Coney Island. And it's suggestive there that phosphorus has declined over the last 15 or 20 years throughout the season, which would all sort of support this picture you're presenting.
Yeah, yeah, and I think it's quite telling that the trends are stronger, certainly in that the Big Traverse and the main channels of Lake of the Woods, where they're more exposed, and that internal loading might be more dynamic, I guess, with resuspension events. So yeah, I'm excited to continue watching.
Good, thank you very much, Caren.
Okay, Todd.
Thank you. All right, David Malahar, I see you've got a question in the Q&A. Would you like to unmute and ask?
Am I unmuted now?
You are.
Oh, good. Thanks, Kelly. And thank you, Caren, for a most interesting satellite description. I used to make satellites, so I'm glad to see that they're still useful.
Excellent.
It appears under the little cartouche on the left-hand side that Whitemouth Lake sort of half covered and half not covered, but you can see that it's got a significant bloom if you compare it to other parts of Lake of the Woods. And yet the Northwest Angle Inlet is nice and clear, and the whole Shoal Lake, Falcon Lake, Westdock Lake are nice and clear, but just take Shoal Lake. Shoal Lake and the Northwest Angle Inlet and Whitemouth Lake, there's this interesting difference. Is there anything to learn from that, or is it just some bad picnickers on Whitemouth Lake?
Yeah, great question again. And there's perhaps others on the call that might be more able to answer that. But I mean, we know, and Todd's hand is up right away. But yeah, we know that the primary source of external phosphorus to the lake is from the Rainy River, and so the main bloom response there is in the main body of the lake, and the watershed impacts on each of the individual sub watersheds, I suspect are very different. But Todd, did you want to?
Well, I was just going to just speak to the Whitemouth Lake situation, and in addition to what Caren said about the south to north flow on the lake, I mean, Whitemouth Lake is an extremely shallow lake surrounded by somewhat marginal farmland, but it's very, very shallow, and indeed in the summer it's got submerged macrophytes almost all the way across the lake. So I'm not surprised that Whitemouth Lake is showing eutrophic bloom, David, in the summer.
This is an independent body of water, just happens to be sort of in the picture, but there's no cross fertilization going on.
No.
Mhm.
Okay, thank you.
We have about 2 minutes left before we're ending today's session. So does anyone else have a question?
If I can throw a question in quickly, there's 2 white streaks diagonally on the right. Is that smoke?
Yeah, so atmospheric effects, so either smoke or aircraft contrails or high level cloud. Yeah. There was some pretty impressive imagery at the beginning of the season that captured the wildfire smoke haze across the lake, though. So.
My assessment of the photograph that you've used here is that this is what it looks like all the time.
Right.
This is standard Lake of the Woods.
Yeah.
Now it gets redder and yellower and bluer from time to time, but it just seems that this is the overall average. It was the same as what Paul Keynes saw a couple of 100 years ago, as Mike Riley was saying. And how do we move it? But we're now observing it real time, but can we link this to a treatment method that's affordable and even feasible?
Exactly, and I think it's important to remember that, yeah, it's been like that for a very long time, and we have now the ability to be able to monitor it and report on it in real time, and sometimes that can be alarming, but it's important to remember that context, I think.
Thank you.
Okay.
Just if I could, it's Todd, add a comment to Michael's question. I mean, I think, and Caren, you showed in an earlier slide the reductions on the Rainy River from Catherine Hargan's nutrient budget thesis work, showing a threefold reduction in tonnage coming down the Rainy River since the 70s with the start of permit regulations after the Clean Water Act in the US, and then additional regulations in US and Canada further. So I think that's the first key to why we may be seeing a glimmer of response from the lake with a 30 or 40 year time lag, that reductions in human loadings was where we've started so far.
Yep, and I think with our method development, we're hoping to explore kind of taking our observations back a few years with other sensors, with like CWIFs. Now that we've developed that machine learning approach that is applied to MODIS, we might be able to kind of extend the time period that we're able to look at that, and I think that'll be quite informative if we can do that.
All right, I don't see anything else in the Q&A and no hands raised that I know of. So I think at this point, we will wrap it up, but please take note of Caren's email, and certainly the opportunity to sign up for the EO Lake Watch. I know I I really enjoy watching the progression through the summer when I get my my notices in. And this summer we were all wondering why it took so long to see any green, but
Right, yeah.
it eventually came. Not that I'm wishing it on the lake, just the timing was interesting. But anyway, thank you so much, Caren, for joining
You're
us,
very
and
welcome. Thank you.
it's fascinating information. For those of you who would like to watch this again, or you have colleagues who missed it, please know that the recording will be up in a couple of days on the Lake of the Woods Water Sustainability Foundation website, where you registered for this, and certainly hope to see you at the next in the series. We have 2 left coming up. And very special thank you again to Caren. This is really has driven our knowledge forward so much on Lake of the Woods. So we really appreciate your time and effort. Thank you very much.
You're welcome. Bye-bye.
Have a great day, everyone.